Hello and welcome everybody. Thank you for taking time to joining us today. And we would like to inform you that that all participants are mute and this webinar will be recorded, and recording will be shared with you afterwards. Please feel free to drop questions in the questions and answers section on the topic, and questions will be answered at the end of this webinar. And in case we exceed planned time, we will get back to those who ask singularly by email after the webinar. So, my name is David Lawrence Nicola, and I'm sales manager by Kistler for the area of vehicle testing. I started by Kistler in 2012 as sales support at the beginning, then as sales engineer for a while up to currently position. I have around about 10 years experience in sales of sensors in different applications. And in this time, I got to know many requirements. And the important question was, which sensor is the right one for this application? So I will drop my contact details in the chat while this session, and I look forward to talk with you after that. So to the content for today, in this webinar, you learn why using accelerometers for vibration measurement. And it's easy of use and efficient, accuracy and robustness, not expensive. So, but the identifying to the right sensor is not always straightforward. And in this webinar, we spoke about how to select the right sensor, the right one for the first time, and requirements and Kistler's accelerometers for automotive and ensuring optimal measurement conditions. Our main speaker for today is Roberto D'Amico. He is a business driver for NVH within the vehicle testing business unit at Kistler. He holds a PhD in noise and vibration from the University Leuven in Belgium, and he has about 15 years of experience in NVH, with particular focus on automotive. And Roberto, I will overhand the words to you.
Thank you, David. Good morning, everybody, or good afternoon, depending where you're sitting today. Let me tell a couple of words about the agenda of the webinar of today. So we will have three main sections that we want to cover. We have the first one is about selection criteria. I want to give you the basic recipe, a quick guide how to choose the right sensor, the right accelerometers. The second section will show you the key requirements for various applications in automotive. So I will drive you through the main applications. We will keep crash out of these application set and right Kistler products that match to these applications. We also have a bonus section. I decided also to include some practical considerations in there, just to give you some basic tips how to make the most out of your test and how to use at best your sensor. Finally, I will wrap up the content of the webinar. Let's jump into the first section. So selection criteria. Now, just a couple of words about the anatomy of our accelerometer. So the accelerometer is basically a sensor which you would connect to the surface which is vibrating and of which you want to measure the vibration. And such a vibration travels through the sensor. It goes to the post of the sensor, which is in turn connected to a sensing element, which again is connected to a seismic mass. And during the vibration, of course, the inertial mass will vibrate and the sensing element will emit some sort of electrical output. Now, we will speak about how this output will be extracted later. But what I want to tell you is that the input vibration, so the mechanical input, is going to be transformed into an electrical signal. And the transformation, this transmission of information, will not be straight. On the other hand, our goal as a sensor manufacturer and your goal is to keep under control the relationship between the mechanical input and the output, the electrical output, because this relation will be undermined by several influences, which can be external. For example, the sensor might be placed into an aggressive environment, and there could be electromagnetic fields or temperature fluctuations and so on. And of course, there are parameters that belong to the sensor design, which might influence as well this relationship. Now, your goal and our goal is to make sure that we keep all these under control. And the first entry point to keep all these under control is the datasheet. So in the datasheet, you find all the information that allows you to control this relationship and to understand how this relationship is built. However, the datasheet is plenty of information, because for us as a sensor manufacturer, it is important to tell you exactly what you are using. And when it comes to the choice of the sensor, this wealth of information can become almost an obstacle, because it creates a longer process for decision making on which sensor you have to use. Therefore, my goal here is to guide you to the right recipe, how to get the right sensor the first time, and what are the parameters you should look at as first, let's say in a first screening process. Let's start that. So the first thing you should look at is the technology. So what type of sensor you need? We have three main sensors for automotive applications. We have charge sensors, which are piezoelectric sensors. Basically, the way they work is similar to what I just explained. So you have a vibration which is transmitted through the sensing element. The sensing element usually is quartz, ceramics. It can be ceramic material, or in the case of many Kistler sensors, it could be a piezo star crystal. And yeah, of course, we will talk about piezo star later, so I'll tell you what this is. But basically, when this element is stressed, it will emit an electrical charge. The electrical charge will have to be carried out of the sensor with cables till a charge amplifier. The charge amplifier will transform the electrical charge into a voltage signal, which can be read and which will be proportional to your vibration. Now, the advantage is that, of course, not having electronics inside the sensor case allows you to exploit maximum temperature for this small construction. So you can usually reach higher temperature than other types of sensors. On the other side, you need to preserve as much as possible the charge, the electrical charge that gets out of the sensing element. Therefore, using long cables is not advisable at all in case of piezoelectric sensors, so charged piezoelectric sensors. The advantage on the other side is that because you have the amplifier outside the sensor itself, you can still adjust the amplification parameter outside the sensor. Therefore, you can set the sensor depending on your application. And now the elements that I've given to you is basically that you have a sensor and the electronics is outside. Now the natural step to move to the next type of technology is to include the electronics inside the sensor itself. And that's how we have IEP sensors, integrated electronic piezoelectric sensors. These sensors are the most commonly used in the automotive industry by far. Why? Because they have electronics inside, and basically you don't have to have it outside of the sensor. Therefore, you can use longer cables, which is very useful in automotive. So you can have even 10 meters cables without having no issues. Of course, the fact that you have electronics inside the sensor case will limit the temperature, the operating temperature of the sensor, because operating at temperatures which are usually higher than 160, 180 degrees might lead to a damage of the electronics. Therefore, your sensor will not provide you, in some cases, not accurate results, but in other cases, really, it could be damaged completely. Another advantage of the integrated electronic sensors is that in the electronics, you can store information. That's how you have TEDs. That option increases the efficiency of your testing setup, because basically your data acquisition system can directly and straightforwardly read information about the sensitivity. And when you have a large test setup, maybe with 100 sensors, it's going to be just a click of your mouse to import all sensitivities of these sensors, rather than having a multiple iterative steps. So these are the key advantages of IEP sensors. So I would say efficiency is the main one, and having long cables. On the other hand, lower temperature ranges are the disadvantages. We have a third type of sensor, third type of technology, which is the capacitive technology, which works substantially in a different way. So you have a sensor, which again is connected to the vibrating surface you want to measure. And this sensor contains a sort of cavity within which an inertial mass is moving. This inertial mass is connected with a spring to the case, and during the vibration of the object you want to measure, the movement of the inertial mass will change the capacitance of the gap in which it is moving. And this is proportional. This is evaluated outside of this cavity, electrically speaking, and is going to be proportional to the acceleration. That's how you measure it. Now, the advantage is that with such a construction, first of all, you can measure frequencies down to DC content, so to 0 Hertz, which is, we will see that is useful in many different situations. Another advantage is that this gap is filled with a fluid, so it's with a gas, which creates an optimal damping condition. With this damping condition, you basically are creating a very linear response, frequency response of the sensor, which permits accurate measurements. And the third point is that the third advantage of these sensors is, of course, that being this inertial mass physically, mechanically bounded by the size of the cavity, it's going to be more complicated, more difficult, let's say, to damage the sensor, due, for example, to a shock. And this is an interesting advantage with respect to IEP sensors or charge sensors. Of course, these sensors will be used in different applications, as we will see later. Now, let's move to the parameters. The first parameter you're going to look at is the measuring range. The measuring range is telling you the maximum acceleration your sensor can measure. And here you can choose it, and you'd better be conservative when it comes to the choice. Sometimes it could be a little bit tricky to identify the type of G range you're looking for, especially if the application is new to you. And here I've included a small table where you can find an indication of the right G ranges you should choose for different applications. Of course, every application is in its features unique, so you still have to consider how much really the object you want to measure is vibrating. You have a dual feature, so characteristic to the measuring range, which is sensitivity, and sensitivity is connecting basically to quantities which are physically different. So it's the output, the electrical output, to the input, mechanical vibration. So you have millivolt over G or picocoulomb over G, and it represents a little bit the transmission from mechanical to electrical content. Now here it is a little bit more. A little bit less intuitive to select a sensor based on the sensitivity, but it gives you an information that in many cases, not in all, is dual to the measuring range. So very usually, in most of the cases, you can choose the measuring range, which gives you a much more direct and intuitive criterion for selection. Another parameter you might want to look at is the threshold, which tells you basically the minimum change in acceleration that will produce a measurable change in the output. So it's a sort of a quantity close to noise threshold. Is basically the minimum amount of vibration you can measure. And in automotive, it is seldom the case that you're going to choose an accelerometer based on the threshold only. Although it's becoming more and more popular, because with electric motors, the vibration is decreasing. And so we are moving the ranges towards lower values, let's say. We will speak about this later. Another parameter which is important is the frequency response. The frequency response basically tells you over which frequency range the response of your sensor is pretty linear. This value is provided in between plus minus 5%, but it can also be provided in plus minus 10% or 3 dB. On our data sheets, you will find mainly the two values. So the two first values, plus minus 5%, plus minus 10%. And as you see in the picture, the typical response of an accelerometer has a region which is rather linear. And if this linearity is in between certain bounds, then this will tell you which is the usable frequency range for that bound. For example, our 8763B250 has a range plus minus 5% in between 1 and 10,000 hertz. And if you go to the 10%, it will go between 0.7 to 15,000 hertz. Of course, it becomes a little bit broader. For automotive applications, it is not common to look at the resonance frequency of the sensor, because usually in automotive, the frequency range of interests are well below, safely below the resonance frequencies of the sensor, of course. There are certain applications in which you might want to have a look at that, like valve vibration, where you have impacts of steel against also metal to metal. But for most of the applications, looking at the frequency range is enough. Then we come to an interesting aspect, which is thermal performance. And here, the parameters you should look at are mainly two. The first one is the operating temperature range, and it's going to tell you the temperature range over which the sensor will not be damaged. So you will preserve the integrity of the sensor over that range. The second parameter is the temperature coefficient of sensitivity. So basically, it tells you how much the sensitivity is changing when changing the temperature. And it is important to look at that when you're considering environments which might have high temperature, higher or lower with respect to ambient temperature, and when you have thermally dynamic environments, like for example, you have temperature changes. Here, I want to introduce the relevance of choosing the right sensing element. So usually, the most common one is the ceramic element, and the ceramic element is generally for temperature application, is not, so for higher temperature or thermally dynamic environment is not that performant. So first of all, generally the IEP, especially IEP sensors with a ceramic sensing element have a temperature range up to 120 degrees, more or less. Of course, the ceramic element, it's nice because it's light, it's small, it gives you a good sensitivity to miniaturize, so you can reach very small dimensions. But if you look at the table, so at the picture on the top right, you'll see that the ceramic has a rather poor performance in terms of sensitivity. This means basically that if the temperature is changing, then the sensitivity will change quite a lot over the temperature range. This means that you're going to have to correct your measurements to make them accurate. The alternative to that would be quartz. Quartz provides you in general, a wider temperature range, but because of the limited sensitivity of the crystal, it will also provide you bigger dimensions. So generally, the dimensions of the sensor will be a little bit bigger. And in terms of temperature stability, you see that the situation improves a bit. So if you're willing to give up small dimensions, quartz could be a good answer to that, to your selection process. There is a third possibility. So Kistler has understood that this was a limitation, so operating temperatures and thermal stability were needed. And we started developing our own crystal, which is called PiezoStar. It's grown in our laboratories. And the PiezoStar allows you to obtain a temperature range which is fully comparable to quartz temperature range. Because it is more sensitive than quartz, it allows for miniaturization, so you can have still small sensors in terms of dimensions, but it offers the best thermal stability on the market. As you see on the picture on the top right, you see that the performance of the PiezoStar is basically flat. at whatever temperature you're using that. This means that if your temperature is changing, or if your temperature is very high, you're not going to have to correct the measurement. You're not going to have to worry about the accuracy of the sensor. And with the piezo star crystal, you're going to have accurate measurement. We have then other two parameters, mass and size. The size is, of course, very important when it comes to the packaging space available to operate. So if you are in an engine bay, you might want to have a rather small sensor to have space also to mount it and so on. You might have also space limitation between components, for example. And this could be an interesting, so size of the sensor is an interesting consideration in this direction, but mass becomes interesting as a sensor is inevitably affecting the dynamics of the object you're measuring. It is just a question of when, so over which frequency range or at which level the sensor will affect the vibration of the object you're measuring. Of course, if you're measuring a chassis of your vehicle with an accelerometer, even if your accelerometer is 20 grams, you're not going to see big impacts on the vibration of your structure in the frequency range of interest, of course. If you're measuring a smaller components, lighter components, having 20 grams of sensor, this is going to have an impact. So the direction here is making sure that the mass of the sensor is sensibly lower than the object you're measuring. Otherwise, what you're going to see is simply, as you see in this picture here, that the dynamics of the object you're measuring is moving towards lower frequency. So this is just the physics of adding a mass to your system. So pay attention to the mass and compare it to the mass of the object you are measuring. It is important also to consider the mounting methods. We have various mounting options, and you have to carefully consider and think how you're going to mount it, because adding a sensor on the component you want to measure, of course, will require to create a connection, which in turn will have a mass, will have a stiffness, will have a damping, and this will affect the measurement. Here you see on left side, you see the main mounting methods with increasing stiffness connection. And on the right-hand side, you see the type of transmissibility you should expect. And you see a little bit, this is qualitative. You see the type of damping effect or the stiffness effect you should expect. Of course, using magnetic base is the softest, allow me to say softest connection method. Then you could have a adhesive mounting base where you might want to glue the base, for example, to the object you want to measure. Then we have direct gluing, or we have screwing with the stud, with or without base, which provides you the stiffest method. And it is important that you reason in this direction, so you try to understand how your mounting method can impact the accuracy of your measurement. Then we have ground isolation, which is becoming more and more relevant. As we measure more and more electrical machine. Here the problem is basically that when the measured object has a different ground from the data acquisition system, the result could be polluted with peaks which repeat themselves at 50 hertz or multiple 50, 60 hertz or multiple of that, and it's going to be pretty difficult to eliminate them. So you're going to be a polluted measure. You're going to have a polluted measurement that can be, that is going to be difficult to correct, let's say. So you're not going to see the actual response of your system. Solutions to that are isolation with a pad. You can screw a pad to your accelerometer, for example, to use a sensor which is already ground isolated, so which has a base already integrated into the sensor. Use material like anodized aluminum, which many sensors have as a main material for the case. And then otherwise you should think about clever positioning of your sensor in a region which is already isolated, electrically isolated. Now, having come this far, let's say that we covered 95% of the features you need to look at to 95% of your choice. Basically, with this information, you can make 95% of your choice. Is this all? Well, yes and no. With these, as I said, you can make most of your choice. But my suggestion is try always to understand other parameters from the datasheet to understand what type of performance you should expect from your sensor. Of course, you might want to look at the housing material, at the type of connector, whether you might need an integral cable, at the presence of heads, whether the housing is sealed, whether the transverse sensitivity of the sensor is at the right level for your application. In some cases, you will not have a 100% match. This could well be the case, it happens. But it is important that you understand how these parameters and how the measuring sensor is going to be impacted by the measuring situation. So the measuring, the application itself, I would say. But I can guarantee you with the information I've given so far, with the parameters I've shown you so far, you're going to be able to select the right sensor rather quickly. And one last thing, of course, if you need further information, feel free to contact us, get in touch with us, and use also the product manual, so the sensor manual, as a reference to get more information about the type of sensor you have in your hands. Having said that, let's move to the second section. So about key requirements for automotive applications and Kistler products. Of course, automotive applications are plenty of instances where you could use accelerometers. You could name thousands, really. I tried to gather them in 4 categories here: engines and powertrains, vehicle dynamics and durability, electric motors and powertrains, structural vibration and model analysis, in which I also put more general troubleshooting or general purpose vibration, let's say. Kistler also provides accelerometers for crash measurements. These I did not include into the overview. And I would say, let's start with the first one, engines and powertrains. So here, the type of requirements which come to the fourth more often are related, first of all, to the G ranges. We talked about 250, 500, 1000 G ranges. The most common is 500 G. Generally, if you have a powertrain application, 500 G is a good starting point, I would say. What is needed is an excellent thermal performance for obvious reasons. An engine is a machine that works at a high temperature, and it requires an accelerometer which is able to measure under certain thermal conditions. Having a rugged design and resistance to harsh environment is also something on which you should not compromise, because when you are placing an accelerometer, for example, in the engine bay, the environment there, it could be rather aggressive. You have grease, oil, you have dust, and so on. So it is important that you pick a sensor which is resistant to all that. Easy mounting might also be an interesting point, because, as I said, in the engine bay, the space could be rather limited. So you might want to have a sensor that can allow you to easily mount it in one direction or in another. And as a last point, easily position the cables. Let's not forget that the cables are part of the measuring chain. And as part of the measuring chain, you need to take care of them. You need to take care of their positions. Typical applications that can be covered with these requirements are engine component measurement, hybrid engines as well, gearboxes, exhaust and radiators, where especially thermal performance becomes very, very important. We have mounting points of engines, for example, or exhaust and motorsport applications. Kistler products which fall in this range are 8766. I have one with me here, so I hope you can see that. So the 8766 is a small sensor, is around 10 millimeters edge. We have it in different variants. Very common for this application are 50 to 150 and 500 G ranges. The special thing about this sensor is that, first of all, it mounts piezo stars, so it ensures excellent thermal performance. best thermal stability on the market, and it has 3 threaded holes. So on each of the sides, you have a threaded holes, which allows you for flexible mounting. So this is very good when you are in a situation where you want to position maybe the axis in a special direction. The sensor is small, light, and it's very rugged, good for harsh applications, and it has TEDs up to 165 degrees, which is very useful when you are dealing with applications with several sensors and want to boost the efficiency of your measurement setup. We have also a sensor which is mounting piezo star. This is 8765. So you have it here. You see it here is also a very compact sensor. This sensor has a through hole, so it has a hole which allows screwing the sensor to the surface, maximizing then the stiffness, the connection stiffness of the sensor when mounting, but also allowing, orientating very easily the cable. So you can very easily pick the direction of the cable depending how you want to place it. And it has an integral ground isolation base, so you don't have to add a pad for having isolation of the sensor, ground isolation of the sensor. And in the end, it has, finally, it has a low profile, so it's very suitable for small spaces, narrow spaces. These 2 sensors are both IEP sensors with integrated electronics, and we have and 3 axle sensors. Then we have single axis sensors, which are 8715, 8714. The first one has ranges up to 1000 G and mounts piezo star crystal in there. So it's very thermally stable, very stable in temperature, and it ensures a very wide operating range. It has a true hole for easy orientation of the cable. Ground isolated pad is integrated, and you have a frequency range up to 15,000 Hertz. 8714, it shares many of the features. You see the ground isolating pad, the through hole, which allows screwing the sensor on the surface if you wish. It's also rugged. The difference is that the 8714 has a ceramic crystal in there. Even though it has such a feature, it can still reach 165 degrees C. So it's suitable for high temperatures, although it does not ensure the same thermal stability as the 8715. It is very used in many applications, like, for example, engines, especially for motorsport, because of its small dimensions, though. Finally, we have 8248 A3, which is not an IP sensor, it's a charge sensor, so it has no integrated electronics. It's a 2000 G range, but of course you can amplify the signal, the charge signal outside with an amplifier, with a signal amplifier. It reaches, of course, 260 degrees C because of this reason, so because it does not have integrated electronics. And thanks to the true hole, it allows easy orientation, so you can orientate the cable the direction you want. Moving to the next application, we have vehicle dynamics and durability, and in terms of requirements, we see that we are moving towards lower Gs. Generally, 2 Gs, 10 Gs, maximum 50 Gs are good for this type of applications, generally not more than that. What is important is having low frequency content, sometimes down to DC. It is important so that you can measure the acceleration at 0 Hertz. Having a rugged design and resistance to harsh environments is also here an important point. As you see in these pictures, you see that these sensors are located outside the vehicle. Maybe you are driving the vehicle on the track, so you might want to make sure that your sensor withstands such a harsh environments, or maybe they are located close to the brake, close to the wheel, or on the underbody of the car. Of course, that's not the case if you want to do some ride quality and comfort measurement from the inside of the vehicle, but still, even in this case, the other criteria still hold. So low frequency range, and generally low G ranges. Typical applications are battery excitation, road load, data acquisition, chassis tests, comfort, ride quality, drivability, handling, and also motorsport are typical applications which can be covered with a general requirements I've just mentioned to you. Here we have mainly two sensors which are of interest, which are 8316 and 8396. They share many different characteristics. For example, both of them are MEMS sensors, so capacitive sensors. We have them in many G ranges. 2, 10, 30, and 50 are the most common for vehicle dynamics and durability. They go down to DC, so they allow low frequency, accurate low frequency measurement because they are capacitive sensors. They are both ground isolated. I actually have an 8396 with me, and it's very nice because 8396 has both ground isolation pad, which is integrated, and a hole for mounting a ground isolation base. So if you can use both of them depending on the situation, how you want to mount the sensor. Both of them allow outputting the temperature, and this is a sort of a unique feature they have because you can also measure the temperature with them, and you can correct your measurements if you wish. The difference between these two is that the 8316 is a single axis sensor, and the 8396 is a triaxial sensor. And another nice thing of these sensors is that you have a variety of options for the outputs. So depending on the data acquisition system you have, or depending on the type of output you want to have, you can configure your sensor and have a bipolar output. You might want to have a unipolar output, or you might even want to have a differential output, which is good for electric vehicle applications, of course. We now move to electric motors and electric powertrains. Here, in terms of G ranges, we stay rather low, I would say. We are around 50 G, maximum 100 G. These are very common G ranges you should look at if you have to deal with these applications. What is important for most of our customers is to have a broad frequency range, and our product ranges allow really to target high frequencies. So you can understand what is happening at higher frequencies. We all know that with electric motors, this is becoming really an important criterion. You might want to have low threshold, meaning low noise, because, for example, an electric motor is going to vibrate not as much as a common engine, let's say, and you might want to be able to measure all that. You might want to have also ground isolation, either with pad or with integrated base. These are possibilities, as well as what you can see here. So you see that what this in this setup was done was putting the sensor on top of a base, which is isolating it from the stand, from the end-of-line stand. Finally, a point of relevance could be the easy mounting of the sensor. Again, here you could be in a situation where space is not much and you want still to mount the sensor properly. So take into account a sensor which allows you to do that, which allows you to be flexible in that direction. Typical applications which are covered by these requirements are electric motors, hybrid powertrains as well, end-of-line testing, which is becoming, of course, very interesting application. Always we see it growing fast. We have compressors, power electronics, and charging electronics when it comes also, for example, to electric vehicles. Generally, these requirements are covering all these areas. Type of products that Kistler can offer in this direction are, first of all, the 8763. 8763 looks indeed very similar to the 8766, which we have seen before. So you see it again here. It's a very small sensor, compact sensor, again with the 3 threaded holes on in the 3 directions to allow flexible mounting. We also have it in different formats, so in different G ranges. We have it 50G, 100G, 250G, and higher. The nice thing for electric application of this sensor is that it allows to measure up to 15 kilohertz, which is pretty interesting for electric applications, as I mentioned before, in terms of requirements. It is again a sensor which is small, light, and rather rugged. And I must tell you that now we even have an improved electronics, for which the noise levels are even lower than what they were before. So it's even a better sensor for electric motors and powertrains. We have an 8764. Again, it's here. It shares the characteristics of the sensor I showed you before. That was the 8765. Again, it has a through hole for easy orientation of the cable, and maximization of the stiffness of the connection with the measuring object, with a measured object, sorry. It has an integral ground isolation base, and like the 8763, it reaches 15,000 hertz. We get very positive feedback from our customers about these sensors for use on electric motors. They really like the fact that it has an integral base and it can cover such a wide frequency range. So 15 kilohertz is really a wide frequency range. You can see quite a lot of things up there. We can also advise to use 8766, which is similar. So it's twin of the 8763, but it mounts a piezo star crystal. So it provides you high thermal stability and wide operating ranges. We have discussed about this sensor earlier. I think it could be interesting in a case where you have a hybrid propulsion system. And then we have 8396. Again, this is a MEMS sensor, but I think it could be interesting for electric mobility because it has a differential output. Differential output is extremely suitable when you have electromagnetic fields, because basically you can it's a good way to eliminate them from your measurements. Even though this is a MEMS sensor, we see that there is a good market interested in measuring on electric vehicles with these sensors. We covered the last application, structural vibration and modal analysis. Here is very generic topic, not only, so it's also troubleshooting, general purpose vibration, as well as more specific as modal analysis. Still low G ranges, but down to 5G, even 10G or 50G. The threshold is important. I mean, having low noise is a very important feature. Having small size and mass, especially mass, can help depending on the object you want to measure. And of course, easy mounting is an important point that you should look at depending on where you're mounting your sensor. Typical applications are component testing, FRF measurements, modal analysis on the body in white, or full body, or as I said, general purpose and troubleshooting. These are common typical applications that you would cover with this type of requirements. And in terms of products, we go back to the 8763. So once again, this ceramic based sensor, which is available in various G ranges, and it ensures a rather broad frequency range. The fact that now we have even lower noise levels allows you to target even better applications like modal analysis, where you really might want to have a low noise level. If you want to move lower in G ranges, but you can compromise in mass and size, you can go with the 8762, which has 3 threaded holes on each of the sides. It's ground isolated. It's a little bit massive because it's 23 grams. But if you place it on the for example, for body model analysis, body in white model analysis, it is not going to affect substantially your response. Otherwise, if you're looking for a sensor which is more compact and lighter, 8788 is a sensor which, because of the design inside the sensor itself, will provide you rather low G ranges, but also low noise and small dimensions. So with this sensor, you're going to be able to perform modal analysis with a rather small sensor as well. Of course, Kistler also offers other type of instruments for modal analysis, for example, or FRF measurements. We have impulse hammer, IEP hammer, impedance head in case you're measuring with so you're exciting with a shaker. And I think it is worth noting that we have cables, but amongst all, we have this 1734 cable, which is many customers like this cable because of the flexibility. So this is really a silicon coated cable which you can basically deform the way you want. If you have to put a cable in narrow spaces, you can see you can actually deform it the way you wish, and then the cable will take the original shape back again without reporting any permanent deformation. This is a feature that many of our customers really love because it gives them the flexibility to move the cable around complex spaces. Now let's jump into the last section, practical considerations. Here I want to give you just some advices how to make the most out of your test. So first point I want to, first suggestion I want to give you is to carefully think where you're mounting the sensor, because this sounds like a trivial choice, but it is not at all. My suggestions are: consider what are the existing information to make a decision. Possibly you have already been through a similar application, so there is past experience, maybe simulations, maybe you know failures and damages for which you know where your sensor should be placed to get you what you need. Compare also always the specs of the sensor with the expected testing condition. Very often what happens is that maybe you thought that the temperature would be lower than what actually is, and then at the end your sensor get damaged because it results that the actual temperature is outside the temperature range of the sensor itself. So keep that into account. Another point is about the mounting location. Consider where you're mounting the sensor, whether it is accessible for the mounting process and for the dismounting process, very important. Consider the type of surface where you're applying the sensor to, the type of flatness, material, and smoothness. It is very important to, of course, ensure an accurate measurement, which is not polluted by the contact between the sensor and the mounting surface, and the possibility of ground loops at the end. So these are all things you need to take into account. Another consideration is about the orientation. Of course, when you will have your results, you will have to interpret them, and there are many applications where it is important that you take into account in which direction your results are displayed. So it is important that you take into account the orientation of the sensor to interpret the results well, or maybe to compare it with simulations. And finally, one last consideration is about the cable. Think well how the cable will be placed in the measurement. It is important that the integrity of the cable is preserved. For example, fatigue tests are one of the examples where cables are often forgotten, and then at the end of the day, one loses the data. So one, because the cable is damaged, one would lose the measured data. So these are the type of consideration I would suggest you to keep in mind. The other point is about mounting the sensors. We have seen earlier some mounting methods. Let's see some details about them. Let's start with the with the stiffest, which is mounting the sensor via stud, which could be with an isolating pad or directly on the surface. It is important that you consider the surface on which you're mounting. It must be smooth, flat, and clean, and keep into account a thin layer of oil if you're planning to go at high frequencies. Keep into account mounting the sensor at the right torque, because if you under torque it, it's going to be the connection is going to be less stiff, and if you over torque it, you risk to damage the sensor. And keep into account that if you're using a scratched pad, you might lose the ground isolation. So have a look at the integrity of your insulating pad, and use always the proper tools to remove the sensor after you mount it. Then we have a direct mounting, so adhesive mounting, which could be done again directly or with the base. So similar consideration as before. Of course, you could use wax, but this is indicated for low G ranges and rather ambient temperatures. If you're planning to go higher in temperature or high G ranges, you would have to use glues. And you can ask us what is the right glue for your application. You can also have a look at the datasheet or the manuals. You will find many suggestions there. The thing that I really want to suggest to you is that when it comes to the dismounting of the sensor, try to use suitable debonding agents, especially when you use the glues. because this will make the dismounting process actually easier and more effective. One final word is about the magnetic base for mounting. Now, magnetic base is nice when you don't have a very strong requirements in terms of frequency, operating frequency range, because of course they are rather soft connection, I would say, compared to the other ones. But it is very practical because you can move the sensor position easily. So you can just detach the sensor from a certain position and move it to another place. However, my suggestion would be careful with this process, because if you just let the base move normally towards the surface, the attachment phase will create an impact which might be even deadly for the sensor. So always approach the surface at an angle and then let the rest of the base move towards the surface to reduce the impact. This will save the integrity of your sensor. One last word, it's about cables. It is important that during the measurement process, the movement of the cable is minimized. And this is very important to, preserve the integrity of this component. If you don't do that and your cable breaks, again, like I told you before, for example, for fatigue testing, the risk is that maybe after a few hours of testing, the signal will not be recorded anymore because you have a problem with the cable, and then you have lost a lot of time besides having lost the cable. So I really invite you to think about that. One possibility is the best thing to do, actually, it's not one possibility. The best thing to do is to tape the cable rather close to the measurement point, minimizing the free vibrating length of the cable. And the taping should take place on the surface you are measuring, not on another one. So if this, for example, is a case where we have a shaker with a sensor on top, here we would have the expander of the shaker, for example. If we would tape the cable on the other side, which is not moving, then this would result in a fatigue test for the cable itself. One last thing I want to tell you is about the connection of the cable to the sensor. Pay attention always to bring together the cable. So as you see here, the cable to the sensor, and then tighten the crown of the cable's connector, and not not the other way around. So don't turn the sensor. It is wrong to do that, because you risk that the pins inside the sensor connector are going to be damaged. So you don't want to do that, and this might happen. So pay attention to that and use it as a suggestion, because it can save the integrity of your sensors and of your cables. Good. Having got this far, I would wrap up what we discussed today. We had 3 sections. We had the first section where I tried to guide you into the golden rules, let's say, how to make most of the choice for the sensors you need for automotive applications. So I gave you an overview of the most important parameters you should look at. Conclusion was that it is important, once you've got to the right sensor, to the right candidate for your application, that you also consider the other parameters on the datasheet, just to understand how they compare to your application. Because it is important that you have an understanding of what is going to be the output of your measurement. The second point we covered were the key requirements. I wanted to give you an overview about the key applications area in the automotive, and what type of Kistler products can support this type of applications. And then finally, we have seen some practical considerations where I try to guide you a little bit with the best practices to avoid issues with your sensors, and also get the most accurate response out of your measurement. So the thing I want to tell you is get in touch with us, contact us, tell us about your applications and how we can support them. We'll be happy to help you find the right sensor. And one very last thing, We will be at the Tire Technology Expo 2022 in Eindhoven in May, and I invite you to, if you are there, to meet us at the stand 2012 in Hall 20. Pass by and we can discuss about acceleration sensors maybe in front of a coffee. And I really look forward to seeing you there in person. With this, I close this part of the webinar, and I open to questions.
Thank you, Roberto, for this very interesting explanation. So let me look. I have any questions. One question is, I have to look on the time. Yeah. One question is, why is the differential output better for electric vehicle applications?
Yes, with this question, I can go back to a slide. Yes. So the differential output basically is made in a way that you have a positive signal and then a negative signal. So usually when you have electric vehicles, you might be worried about the influence of electromagnetic fields, which might perturb your measurement. In general, our sensors have a pretty good behavior under electromagnetic fields, but the differential output will allow you first to sum the impact of the electromagnetic field and then to subtract it. So basically at the end, the signal you're going to measure on the data acquisition system, it will be rather clean from this type of noise, which could well happen also in normal cases where you have very long cables, for example. Differential output is also indicated for those.
Okay, good. Thank you. And the second question is, what is the noise level reached by the 8763 sensor in its new version?
So basically, sorry for not mentioning this during the presentation. At the end of 2021, we have increased the noise level by about 30%. So we moved from around 400 micro G to 290 micro G for the 50 version, for example. Therefore, these are the noise levels. And I must tell you that we witness with the stabilization of production of these new electronics, and even lower levels. Of course, take these numbers, which should be already in the data sheets you find online, as indicative numbers, but it is likely the case that you are going to get even lower performances than that. And this makes this 8763 sensor, as I said during the presentation, even more interesting for e-motor applications, for example, motor analysis or FRF measurements, where, as I told you, the noise level could be a differentiating feature. So a low noise threshold could be really a differentiating feature.
Okay. Thank you, Roberto. And then the next question is the deviation in terms of thermal sensitivity really influent on measurement accuracy?
Yes, absolutely. It is. It is. And you would be surprised to see how much it can influence your measurement. So if the response is not thermally stable, so let's go back to the slide. If the response is not thermally stable, you're going to have to account for a variation in your sensitivity. And then, I mean, if you have a variation in temperature, you will not know what is the right vibration you're actually getting there. While if you have, for example, a piezo star, which is a stable thermally stable crystal, allows you basically not to worry about how temperature is changing, but just getting your results and analyzing them. And you know, if you want to do a very simple exercise to understand it, you can take a ceramic sensor next to a piezo star sensor, put them on a shaker or on a known source, and use a simple hair dryer, which will increase the temperature of the two sensors at the same time. You will see that there is a difference. And of course, if you want to have a look at the piezo star, just contact our sales and we can arrange visits to show you the benefit of that. But you can do this test to see how much a change in temperature is going to affect your measurement.
Okay, thank you. So, and the last one is, we have less minutes. What type of sensors would you advise for high voltage regions of an electric vehicle?
So high voltage regions, I would say that these regions might be impacted by some sort of electromagnetic influences or electrical influences. Possibly, I would consider 8763, as I mentioned to you before. So this is a sensor which can be mounted with a pad to ensure ground isolation. Otherwise, the possibility would be with the 8764 that I also have here. This has an integrated ground isolation pad. It also has a through hole, so you can screw the sensor directly on the surface to ensure maximum stiffness, connection stiffness. Otherwise, a possibility, as I mentioned earlier, would be 8396. So this is a MEMS sensor with differential output for the reasons that I mentioned before. As I told you, it is as a ground isolation pad on one side, and it also has a threaded hole on the other. So you can also use a pad to screw it with the stud on your surface. But with the differential output, because for what I explained before, this is particularly suitable for electromagnetic field, the presence of electromagnetic field. What I have to tell you, of course, is that if you're going to use a MEMS sensor for such a measurement, the frequency range is going to be limited. While if you're going to use, for example, an 8764, this sensor reaches 15,000 hertz. So it's at 10%. So it's covering an extremely wide frequency range, which is also the reason why many of our customers really use these for for measurements on electric machines. Even if they don't screw it, maybe they glue it, so they don't exploit fully the stiffness of the connection stiffness. But still, this is a very good solution for that.
Sure. Yeah. Okay. Thank you, Roberto. So we must come to the end of this webinar, of this session. We have a lot of more questions, but we will answer after this webinar all open questions to all participants. So yeah, Roberto, thank you. Thank you for this very interesting webinar, and thank you all for joining us today. And I hope this session is very useful for all. And I wish all the best, and have you a nice day. And please feel free to contact us for any questions more. My contact details are in the chat. And yes, so, and have a nice day, and thank you for joining us.
Thank you all.
Bye-bye.
Have a good day. Bye-bye.